Module 1B, the Sky and Seasons, and we're talking about the celestial sphere in this submodule. We're going to discuss the celestial sphere, and I won't give away too much because there's a couple little videos that will talk about it, but notice the projection of the Earth's North Pole out onto the sky, for example. So we have various markings on this imaginary sphere that all the stars are on, and it's a very useful model for understanding and talking about the sky.
To understand the idea of the celestial sphere, first think of the Earth in space. The stars all around us look as if they could be on the inside of a huge distant sphere. Though the stars are really at different distances, this idea of the celestial sphere is very useful for giving positions in the sky. Now imagine you are close to the North Pole. Here, it is like being on a roundabout because the Earth is spinning on its axis once a day. Every day, each star circles all around you and around the point overhead, which is the celestial North Pole. There is, of course, a celestial South Pole as well, and the celestial equator circles the sky halfway between the poles. Positions on the celestial sphere are specified by two coordinates. Declination, like latitude on Earth, is measured in degrees north or south of the equator. Positive declinations are north, negative declinations south. Right ascension, the equivalent of longitude, is measured in hours from a zero line. An hour is 15 degrees. Because you are on the Earth's surface, half of the sky is completely hidden. The Earth gets in the way and creates your horizon. In effect, your personal sky is like a hemispherical dome. Imagine now you move to the Earth's equator. The celestial equator runs from east to west through the zenith, the overhead point. The celestial poles are due north and south on the horizon. The north-south line on the sky through the zenith is called the meridian. At an intermediate latitude, the altitude of the celestial pole in the sky is equal to your latitude on Earth. Some stars are circumpolar and never set. It's sometimes useful to know a star's altitude, its height above the horizon, and its azimuth, its compass direction. Azimuth is measured round the horizon from north, but as the stars move, their altitude and azimuth constantly change.
To get our coordinate system going on the celestial sphere, we first project out Earth's equator onto the sky, and that is the celestial equator on the sky. Earth has a North Pole, but then you project it out onto the sky, and that's a celestial pole. The North Celestial Pole above the North Pole. Notice how the ecliptic and the celestial equator have a 23.5 degree tilt. You can see them lined up here on the celestial sphere. 23.5 degrees, that's exactly the tilt of Earth's axis compared to its orbital plane around the Sun. So, what that means is, although the celestial equator is always in the same place in our sky, day and night as the Earth rotates, the sky moves above us, but the celestial equator is in the same place. Not so for the ecliptic, and this will lead to the seasons that we'll be discussing in the next submodule, where the Sun is always on the ecliptic, so it's higher in the sky in the summer and lower in the winter.
Okay, so this is a model of the celestial sphere, and it's really hard to get an idea of what's going on without seeing it, and I can't even tell you if this is showing up the camera because I covered up the video because I can't stand to see myself, just to let you know. So the goal of the celestial sphere is to somehow picture the sky, and in this model it represents all the stars as being on this shell surrounding the Earth. Now clearly that's not the way it really is. These stars are not all the same distance from the Earth, and they're not this close. But since they're so far away, and their motion in the sky is due to the Earth's rotation, and I could rotate the Earth like this. There's a little knob in there, and I can rotate it. Then it's a great way for us to model what's going to happen, and it can tell us a lot of stuff about the motion of the sky. So imagine we're in Louisiana. That's where I live. So I'm going to turn this so that North America's right there, and I'm going to put it like this, so that if I was standing on this, this would be straight up, and this is what I would see at night. These stars right here. One thing you'll notice is that if you live in Louisiana, you can't see everything. Okay, the stars over here, I will never see those, because if you look, imagine a flat plane of the horizon right around here. I can't see anything below this line, essentially. Okay. Also, notice what happens during the night. I'm going to hold the Earth still and rotate this. Okay. Let's see, wait. East to west. That's right. Okay. And so this point up here, if you were looking there, like that, those stars would just rotate around like that. And that's exactly what you see. You see a point, and this is the north, where the North Star is, or the North Celestial Pole that everything rotates about. If you were at the North Pole, it would look like this, and there would be a star straight above you that doesn't move, and everything rotates like that. You'd see a star right by the horizon, and it would just rotate all around. During the day, you couldn't see it because it's too bright. The other nice thing about this model is it also has this representing the motion of the sun, and you can see that it's not on the same axis of rotation as the Earth. That's because the Earth, as it goes around the sun, its axis of rotation is tilted. So you'll see here, it's kind of hard to see, but this little other dotted line, this its little marked line, this tells you the path of the sun on the celestial sphere if you mapped it on there. And this is called the ecliptic, and it's tilted 23 degrees, just like the Earth is tilted, its axis. So if you look at during the summer, this is during the summer, the sun's on the north side of the celestial sphere, and see the northern hemisphere gets a lot more sun and it's warmer. And in the winter for the northern hemisphere, it's down here. Okay, so you can see that, and you can put it at different dates. And so a given day, let's put it today, which is June 3rd. I'm going to put this on June 3rd. My computer's getting angry because I'm doing a lot of things. Okay, June 3rd is right. Looks like I go around. June 3rd right here. Okay. There's June 3rd, and I'm going to put it back on Hammond, Louisiana. Right there. And you'll notice that the sun is not straight overhead. It's not. Okay. And during the day, it would start like this. The sun would rise. It would go across. It doesn't go straight overhead, you see. It comes back down. And then it sets. This is setting because now it's below the horizon. And now here are all the stars that we can see. Okay, and they rotate through the whole night, and then the sun rises again the next day, and the sun's in a slightly different location. You'll notice that these are up during the day and you can't see them, but during the other half of the year, the sun's over here and you can see these stars, but you can't see these stars. So that's the celestial sphere. I'll show you some more pictures in my lecture, but it's good to see the actual model of it. This also has, you probably can't see it, but the Milky Way, which no one ever sees anymore because of light pollution, but that's enough for now.
This is graphically why you have to have a different star chart for every month of the year. We talk about how the sun keeps moving. It's really because Earth is orbiting around the sun, and the sun is blocking out different stars, sweeping out the ecliptic across the sky. The because of this, we talk about seasonal stars, stars that you can't see certain times of the year. Look for May on this image. In May, you can easily see Libra at night, but you can't see Aries at night, or Taurus. You can see Scorpio in May. So it depends what time of year as to which stars are easy to see at night and which ones are completely blocked by the sun. Notice where Leo is. If you want to see Leo, September's not a good time to do it. The sun would be in Leo in September. What this means is there are certain stars you cannot see, certain constellations you can't see. For example, Gemini is difficult to see in the summer. That's near my favorite constellation, Orion, so you can't see Orion in June. That's true no matter where you are on the Earth, so don't be fooled that you could go to the southern hemisphere and see those same winter constellations during their winter. It won't be possible. If the sun is blocking out certain constellations, it's blocking it out for everyone on Earth. The sun follows the ecliptic, and everybody on Earth will see the sun against those same stars. We need a coordinate system so that astronomers can talk to each other about exactly where an object is in the sky. We're going to talk about the equatorial coordinate system, right ascension and declination. It's just like longitude and latitude on Earth. Well, at least it's very similar. In fact, when you project out the Earth's equator onto the sky, you've got a start for this system. The right ascension is like longitude. Longitude is those long lines on Earth. And if you look at this picture, there's a long line and it says declination on it. But it's not saying that's a declination line. It's showing that declination increases as you go up that line of right ascension. So declination is the lines that are parallel to the celestial equator. You see sort of the blue plane there. The celestial equator is 0 degrees of declination, and the declination lines go up parallel to that, following the arrow in the diagram that says declination up, and the declination goes from 0 at the celestial equator up to 90 degrees at the pole. So the declination is measured in degrees. The right ascension goes around and it's measured in hours, because as the Earth rotates, different part of the sky keeps going past, and in 24 hours then we start over. So the right ascension is measured in hours and goes from 0 to 24, and these are coordinates on the sky. On this little celestial sphere you can see a star, the blue asterisk. What are the coordinates there? The coordinates would be right ascension of some number and declination of some number. And you can see the declination is how high up it is from the purple celestial equator, and then the right ascension is measured over from a point that is a 0 point for the right ascension. Turns out that 0 point is the vernal equinox, which is where the ecliptic crosses the celestial equator. But I just want to make sure you understand these coordinates are attached to the stars, and the right ascension is how far it is around the sky, and the declination is how far it is up, basically from the southern horizon. But declination is measured from the celestial equator, and right ascension is from a 0 point that is somewhere along that celestial equator. The North Star is right above the North Pole, putting it in a very special place.
The North Celestial Pole sits in the northern sky, and the elevation of the pole, or the bright star Polaris, is the same as your latitude on the Earth's surface. Some stars are visible throughout the night as they orbit the North Celestial Pole. They are called circumpolar stars. If you were positioned at the Earth's equator, stars would appear to rise directly out of the east and set directly into the west. The North Celestial Pole would be down on the horizon. That represents the region around which the stars are rotating in the night sky. If you move to the pole of the Earth, the North Pole of the Earth, the North Celestial Pole will be directly overhead. Imagine yourself standing on the top of a spinning top, staring upwards. All of the stars would be circumpolar. Those near the horizon would be orbiting parallel to the horizon. and all stars would appear to circuit around the north celestial pole or the star Polaris, which would be directly above your head.
In this module, we talked about the celestial sphere. We talked about how you project out Earth's equator onto the sky, the north and south poles onto the sky, and you get the celestial equator and the celestial poles, which are on this sphere surrounding the Earth. We use those marks to determine a coordinate system that's kind of a mirror of longitude and latitude, and we found that the ecliptic is on the celestial sphere, but it's tilted because of the way Earth's axis is tilted compared to its orbit around the Sun.